Okay, let's see another example. A manufacturer wants to design a cylindrical container to contain 300 pi cube centimeters of water. We want to determine the height and radius of the base, so the manufacturer will use as little materials as possible. This is another example of an optimization problem. Here, the thing we want to minimize is the amount of the material. We want to use as little materials as possible to design a cylinder, so such that the cylinder will be able to contain 300 pi cube centimeters of water. In other words, we want the volume of the cylinder we design to be 300 pi. And because the material we use depends on the surface area of the cylinder, right? Because the bigger the surface area is, the more material we're gonna use. So to minimize the amount of material is the same to minimize the surface area. Therefore, we want to minimize the surface area. Okay, before I show you how to solve this problem, I want to show you a similar problem. All right. So in this problem, we are given we have another situation, which is we are given the surface area, and we want to use the given material to build a cylinder. So the cylinder will contain as more water as possible. Now this graph shows us the volume of the cylinder we design by using different radius. For example, if we decide that the radius is 0.6993, so the cylinder we build will look like this, and at this point the volume is 14.25. And if we choose the radius as 2.45, then the cylinder will look like this. It's like a pen, right? And at this point, the volume is 7.41. According to this graph, if we wanted the volume to be the biggest, if we wanted the cylinder to be able to contain as more water as possible, we should choose the radius to be 1.50, around 1.50. So the volume, the maximum amount of water the cylinder can contain is about 22.27. Okay, let's go back to our problem. So we want to minimize the surface area, and given that the volume is a constant, the volume is 300 pi. So to solve this problem, first we need to know what is the geometric formula of the volume and the surface area for the cylinder. The formula of the volume is pi r squared times h. So here r is the radius of the base, and h is the height of the cylinder. Now the surface area equals 2 pi r squared plus 2 pi rh. The reason is because if we cut the cylinder into 3 pieces, so these 2 pieces are the top base and the bottom base, and they are both circles. And these 2 circles, they have the same radius, so the area of each is pi r squared. Now the middle part, after if we cut from here and then we extend it, like if we unroll it, we will get a piece of a rectangular area. Because if we cut and then we unroll this, so this will be okay. So we will get a rectangle. Okay, so in this rectangle, as you can see here, the width is the height of the cylinder, and the length is equal to the circumference of the circle. And since the radius we said is r, so the circumference is 2 pi r, so the length is 2 pi r. So therefore, the surface area is 2 pi r times h, and plus the area of the 2 circles. So that's why we have 2 pi r squared. Okay. So we want to minimize this quantity given that the volume is 300 pi. So in this problem, the constraint is that the volume pi r squared times h, this is equal to 300 pi. So in other words, r squared times h equals 300. Because in this quantity, we have 2 variables. One is radius r, another is the height h. According to the strategy we saw in the previous video, we wanna reduce the number of variables into 1, and we can do that by using this condition. Since r squared times h equals 300, so h gonna be 300 over r squared. Therefore, to minimize this quantity is equivalent to minimize 2 pi r squared plus 2 pi r. Now I write h in terms of r using this equation. So this will be 2 pi r squared plus 600 pi over r. Okay. So now we go back to calculus. So this is like we have a function f of r, and we wanna find what is the minimum value of this function. Okay. So first, let's look at what is the domain of this function. Because R stands for the radius of the cylinder. Now, when we choose the radius can be as small as possible. But remember, it cannot be 0, because if it's 0, the cylinder will not exist. Therefore, when we consider the domain of R of the function, it starts from 0 to infinity, to positive infinity. Okay. Since we're looking for the minimum value of the function f of r, we start taking the derivative, so we can find the critical points. So we take the derivative of the function with respect to r. Now the r is the variable, so the derivative of function is a 4 pi r plus minus 600 pi over r squared. Okay. And then we let the derivative be 0. So we have the equation 4 pi r minus 600 pi over r squared equals 0. If we multiply r squared on both sides, we're gonna have 4 pi r to the third equals 600 pi. And we divide by 4 pi. So we can get r to the third equals 150. So r equals the cube root of 150. Now, because since 0 is not in the domain of the function, therefore 0 is not a critical point. Even though the derivative does not exist when r equals 0, but since 0 is not in the on the domain, so here we have only one critical point. Okay, then to find the minimum value, we divided the domain by using this critical points. Now the cube root of 150 is around 5.31. So the two test points we choose, so one is less than 5.31. I choose 1. Another one I choose 10. And then I plug these two numbers into the derivative. When r equals 1, the derivative is a 4 pi 1 minus 600 pi over 1. Now this is a negative, so the function, since the derivative is negative, the function is decreasing. And when r equals 10, the derivative is 4 pi 10 minus 600 pi over 10 squared. Now this is equal to 40 pi minus 6 pi. That's positive. So the function is increasing. Therefore, the function has a minimum value when R